right, if I show you the screen, you can see that we are going to talk about how two things today. And if I turn on the projector, you might actually be able to see, but the first line says, while it's warming up, manganese changes everything through making oxygen. And then the next part is going to be oxygen changes everything. But you're going to see in this, what I want to do is I want to actually show you a little more detail, first about manganese and then about redox potentials, because we covered those in Chapter 5. And they are central to how R.J.P. Williams thinks. In fact, if it wasn't for redox potentials, he probably would not have developed his ideas at all. But redox potentials allowed him to see a ranking of things. And the ranking by E values is a good way that chemists think. And so if you can just take that away, I'm going to ask test questions about, do you think by E values? And probably there'll be some that can you calculate by E values. But I'm actually more interested in that you can think qualitatively by E values and understand why R.J.P. Williams made his argument. One of his arguments was that manganese was pretty unique chemically. In other words, there's no other path really to unlock oxygen on a wide scale than by getting it from water. But getting it from water is hard because water holds on to its electrons very tightly. And to remove the electrons from water is one of the hardest things to do. In fact, only manganese can possibly do it. So the way that chemists think is one of the ways is that they think about how each metal has a binding different personality. After you study enough of these things, that's what R.J.P. Williams did. He studied lots of chemistry and he noticed that, copper always binds things tightly. But they also have different kinds of ligands that they usually like to bind. The R.J.P. Williams series, some of the graphs that we show earlier in the book are good for oxygen, nitrogen, and sulfur, things like that. But if you zoom in a little more, you can find some preferences, like the different metals just bind well to other things, like sodium and potassium don't bind anything well. If anything, they bind oxygen donor ligands. For example, if you see a potassium in a protein structure, it's going to be surrounded by oxygens. And in fact, you can even predict which geometries will be preferred. And again, this is always on a scale. You can find examples that break the rules. But the main thing is, this is not an argument where it's knocked down if you find one little example that breaks the rules. It's based on probabilities. And the thing is, most of the metals like to bind tetragonally, like copper likes to bind tetragonally. Once in a while, you can see a 5 coordination. But other ones like to bind octahedrally. And so iron and cobalt both like to bind octahedrally. And you see right there that iron and cobalt are both found in the heme group doing the same kind of thing. If you look at vitamin B12, which has cobalt in the heme group, porphyrin group, I should say, and iron, which is in the heme group, contains iron in the same geometry. The fact that both metals can fit into the same place in the middle of a porphyrin ring is reflected here. And you can actually even extend it to say, hey, I wonder if artificially I can make in the lab a chromium porphyrin ring. And so you look at these and you come up with things. Now let's look at manganese specifically. Manganese and iron are very close together, but they are kind of opposite. They have definitely different features when you get around to it. Iron goes from +2 to +3. Manganese can go from +2 to +4. That's what it prefers to do. And just that little difference, along with the minor differences in their geometries, well, you see their geometries are actually the same. But you can, as you get to be a chemist, you can come up with these things. I've seen iron doing this a lot. Iron likes to bind this atom in this way. And so if you're making an iron binding site, each of the metals has a different kind of personality. And so you have the lineup with the different suspects. This is from the movie The Usual Suspects, which is one of those movies that I do want to see it again, because it's actually got some depth to it. But it's basically a mob movie, and you know that one of these guys is the bad guy, but you don't know which one. And so you have them up, and you see they have different heights, they have different personalities, and one of them's like whatever the different jobs are. But the metals are like that. They have different personalities, and they can be forced into something that's suboptimal. But really, you want to have them doing the best situation is where they're doing the job that they're made to do. So you can look at this, and this is one of the ways in which the personalities are actually summed up. I'm mostly showing this so that someday, if you're interested, what did R.J.P. Williams think that this metal was? You can go back to this and get the chemistry side of their personality. Just want to remind you that some people in this room are probably going to be doing some of these metals. And if you go back to this rule when you're making your talk, you can make sure that you're talking about chemistry as you're doing it. If you're talking about the personality of calcium, for example, right there. So as you're thinking ahead to your presentation, be thinking about, make sure that you get the chemistry in there to show that you're thinking like a chemist, thinking like R.J.P. Williams. And this is literally his words, so you can show it by quoting this. And there's even protein design projects in here. If you make a site that likes to bind manganese, but it doesn't like to bind calcium, can you do that? And sometimes their personalities are pretty close, and so they might not be selective. It might bind both of them. I think it's kind of fascinating to think about how do these different puzzle pieces fit together. But the main thing we want to talk about at the point at which oxygen gets unlocked is manganese itself. And so this is from an article about, here's the title of the article on the next page. Oh, I have animations. How manganese empowered life with dioxygen, and how dioxygen empowered manganese. So you see how there's sort of a two-ways thing going on here. And the thing I want you to point out is, as usual, we have the past on the left, the present on the right. And as you're moving from billions of years ago, you are moving up in voltage, in E value. And this doesn't really make sense to someone who hasn't gone through chapter 5 yet. But chapter 5 talks about how we can organize these things by their redox potentials, and the stuff on the bottom will react with the stuff on the top. So the cool thing is, you can see that, remember that these are arranged by reduction potential. So it's kind of like, how hard is it to reduce it, to pull oxygens off of it and to have it reduce something else, okay? So how hard is it to oxidize? That would be another way to talk about it. So iron has a redox potential in the range. I mean, you can go from iron 2 to iron 1, iron 3 really is what you do. And you can shift it around by changing its environment, putting it in a heme group, or surrounding it with oxygens instead, or things like that. And it will change its voltage a little bit, but really pretty much it's going to change from -3 to +3, which exactly fits with the old kind of Earth. If you follow the blue line is the redox potential of the whole Earth environment. Okay, so on the whole Earth, early on, it was very reduced. And so we were at the very negative top of the redox potential. Remember, it's reduction potential, ability to reduce something else. So if you're already very reduced, you're not going to be able to reduce other things. But you actually expand the oxidizing potential of things as it goes along, and as anoxygenic phototrophy shows up. And that actually involves manganese at some level. So I want to show you that on the next slide. This is the idea that you can have a photosystem that captures light, and then what does it do with that energy? Well, if it's on a protein that binds manganese too, it actually can pass that to the manganese. The energy can be caught, passed to the manganese, and it can cause an electron to be dislodged. Basically, it can oxidize the manganese. And notice that if this happens on the outside of the cell, it actually results in the whole Earth being oxidized. And this is, the cell needs electrons, and so this is a benefit for the cell. The light is basically free money for the cell. It basically just has to have something colored that will catch the light, and then if you arrange it right, the energy can actually be funneled onto the electron of the manganese to pull it off. The end result is the cell gets electrons, and manganese becomes oxidized outside the cell, where the Earth eventually becomes more oxidized. So that's what they're saying about how manganese oxidizes the Earth, but then oxygen helps manganese, because as oxygen is produced, there's more oxidized stuff outside, and the cells get more and more electrons. As they grow, they're hoarding electrons and they're ejecting oxygen or oxidating equivalents. And so what you have is you have actually the reaction centers at the middle of the photosystems. I don't know how much they cover this. If you've taken plant biology, you might have talked about this, but I don't know how much we cover this in Biochem 2, and it's not a prereq for this class. But the very center of plants' photosystems are reaction centers, and it looks like those evolved first, and those look like they could do this kind of thing before you have the full power of manganese unlocked. Realize that this only requires manganese to go from +2 to +3. And so as the Earth oxidizes, then you actually move into manganese's range. And when you actually go to manganese's range, when you produce manganese +3 is actually such a powerful reductant that it can even reduce water. And you can see the water's up here in this range, 0.8 if you're talking about going to oxygen. This is the important thing. You're pulling electrons off of this to make oxygen. You're using the electrons, and you have a plentiful electron source. It's just very hard to unlock. And manganese can help you unlock it because manganese is below the manganese 3 versus manganese 2. So you can actually start to produce manganese 3 from light, and then as you produce more and more oxidized manganese, the manganese can help you oxidize, or the manganese can help you pull electrons off of, which is to oxidize water itself. Notice how the terminology works. You're producing oxygen. So you're literally oxidizing water because you're turning it from H2O into O2. You're turning it into oxygen, so you're oxidizing it. That means that the electrons are pulled off, and they have the power to go on to anything above them. So look at all the things that the electrons can go on to once you pull them off of oxygen. It's just that you need something more powerful than oxygen, and the only thing that's not involving oxygen itself is way down here, manganese. This is how manganese opened up. As manganese got oxidized, it allowed the Earth even to become more oxidized and to produce more oxygen. And so life literally produced oxygen, the most powerful oxidizing agent of all. Well, I have to take that back, but it's a technicality. And the main thing is manganese's E-value range is all in this range right here. Once you get it oxidized enough to be below oxygen, then you can do real photosynthesis. So if you look at this, this is how it started, and this is how it works now. Oxygenic photosynthesis actually looks like manganese phototrophy, which I think I call this manganese photosynthesis. I decided to use a simpler term in the book. Iron photosynthesis actually can work this way as well. It's just that manganese photosynthesis, you can see that it eventually produces manganese 4 in clusters that can actually make oxygen. And that's the one thing that's powerful enough to do it. This is one of those predictions that I would make about aliens. I believe that aliens would probably work on manganese. There's nothing else that's really abundant enough and redox powerful enough to be able to deal with oxygen in this way. Before that happens, actually manganese has other benefits. Manganese actually is a redox balancer because manganese is sort of weird because it can go back and forth. Its energies for going back and forth between 2 and 3 is actually kind of weird. I don't have this in there, but 3 is less stable. I do have it in text up here. Manganese 3 is actually not stable. It's more stable for manganese 3 to produce manganese 4 and manganese 2. It kind of disproportionates is what they call it. And so that means once you have manganese 3, you eventually get manganese 4 a lot easier, and manganese 4 is what the photosynthesis uses. But the other side of things is as manganese 3 goes to manganese 2, that actually protects, and it actually ends up protecting you from bad oxygen species. So manganese protects you from the bad side of the oxygen it's producing. If it's just in ions, it will actually react this way. You can get to the redox potentials of how that works, but essentially it's in the range that is low enough to interact with oxygen again. So it's a little bit of a shield, and at the end of the day, also it's literally a oxygen catalyst. And you see right here, this is the O2 to H2O that's happening in the photosynthesis. But you can actually use it without light energy in other enzymes. Once you have a lot of oxygen around, you can actually take it and you can run the other direction with it if you're running the other direction with manganese as well. So manganese is very useful for catalysis on top of everything else. All that means is that manganese does a lot of stuff, but this is the crucial thing that it does. And to me, it doesn't seem that far-fetched that this could evolve. What happens is if you have two manganeses of the right oxidation state next to each other, just held together on a protein, and you have some energy input into the system, the energy input can sort of be channeled through the manganeses. The manganeses will naturally bind some form of oxygen, especially H2O, but before that it could form other forms of oxygen or maybe even H2S. Manganese likes to bind oxygens. And if it binds two oxygens, then it holds them together. Those two oxygens can bind each other and form O2, which is the crucial molecule happening outside the cell, and it leaves. Now, it requires energy because it's hard to take the OH2 and to rip the protons off. But if the energy just helps you to disrupt that structure, you've already got two oxygens next to each other if you've got two manganeses. And so you can see how this could develop. All you need is a way for energy to get into manganese. And you have old proteins in which energy gets into manganese. It just makes manganese 3 instead of making O2 but from bound oxygens. So this is the picture I want you to have in your mind. I want you to see how an enzyme could develop this way. Now the whole problem is H2O is very stable. It's kind of like good news is very abundant, right? Bad news is very stable, so breaking it apart is hard. But once you figure out how, basically you have an advantage. It's like the killer app or whatever the business term is for the advantage you have over your competitors that allows you to expand your business. The business that was developed on manganese allowed life to really proliferate because the oxygen that was produced, and again, the oxygen looks bad at first, but then it actually does bad reactions at first, but you protect yourself against the bad reactions, and then more and more good reactions happen. So can this actually happen? And this is one lab that's actually done some form of manganese where they just take the manganese. This is not in a special, they just take a non-light-driven manganese metalloenzyme. And basically, first of all, they actually took the bacterial photosystem. They just found the photosystem didn't bind manganese. And they said, what if we put a couple mutations in there that made it bind manganese? They fit manganese's binding personality. And so they added aspartate, glutamate, and histidine. I think that those will go along with the personality of manganese on the previous slide. And this wasn't the hard part. This wasn't that hard for them to figure out how to make a manganese binding site. And so the manganese binding mutant would actually be able to go from manganese 3 to manganese 2 and to basically absorb an extra electron from oxygen. Again, it does this just in solution by itself, but it does it now next to a protein, both allowing the electron to go wherever the protein wants it to go and producing oxygen. So they basically, by taking a photosystem that was not oxygen generating, I'll just say it that way. So if you have an O2 generating, basically something that wasn't O2 generating was made to be O2 generating by binding manganese to it, and the only thing is it was already set up to collect light and to use the light energy to allow the manganese to sort of extract the electrons. It was surprisingly easy. It was light-driven oxygen production, and the only other thing is it's not from water, it's from superoxide. So you'll notice that that's a little different. It's a little easier to pull electrons off of superoxide than water. But you've got like 2 of the 3 things that you need to really have photosynthesis going on. That's pretty good. So yeah, that's pretty powerful. That's pretty powerful. And it passed the electrons. It was able to pass the electrons off to the electron transport chain that it was already set up for. So yeah, this is the other thing that we can look at. That's what happens if you just put one manganese onto a photosystem. What if we look at the existing photosystems that have manganese in them? and look and see what they are, and take just the manganese cluster, because the manganese there is in this weird cluster. You have 3 manganeses, you have this sort of outlying manganese, and then you have a calcium. It kind of looks like a rock. If you look at this, it looks literally like a crystal structure that you would see in geology. But if you just take this out of the protein, artificial complex, what can it do if this is floating around in solution, like it might be from some minerals? And so that's what they did. They actually were able to make it from simpler precursors with manganese precursors. And this is, I believe this is a permanganate. This isn't going to be necessarily floating around. This is not like stuff that's going to happen naturally. But it's conceivable that it could be built up naturally if you can build it up from simple things like this. So they just reacted it, froze it, and then they recrystallized it. So it's a very simple technique, and then it makes this complex in which the only real thing that looks like a protein is this little ring hanging off here. And that would actually be able to cycle through the different oxidation states of manganese. And by the way, notice these are all high oxidation states. These are not going to be accessible until you have the whole environment being fairly oxidized already. See that +3 and +4 requires some +4 manganese. Once you have these though, these are able, and just this little complex that they made with the little ring hanging off, it was able to take oxygen and to basically produce oxygen just from that. This is cyclic voltammetry. This is covered in Dr. Pierce's electrochemistry class. Did anybody take that class, by the way? Electrochem? Did you? Or you're going? Okay. Oh, perfect. Okay, so I don't know if she shows stuff like this from time to time, but definitely this is electrochemistry. When I was in high school, I actually did a summer chemistry program, and I did this. Since then, I have never done this because I never took an electrochemistry lab, so I'll have to ask Dr. Pierce about it someday. But according to them, this shows that the oxygen is being produced by the electrons moving through the manganese. So because of manganese, basically because of this, energy was able to be stored. In a sense, the energy was stored in oxygen's chemical potential and the ability for it to cause combustions to happen. Remember the why is fire hot paper. And if you have, basically you have the earth, and the earth is a bunch of chemicals, and they can react. Over time, they can react, and they sort of will run out of steam, an exponential decay. That's sort of a chapter 6 concept. But if you have energy coming into the system, photosynthesis can actually cause the net energy capture by Earth to stop going down and even go up, because you're taking energy from outside the Earth and you're capturing it in chemical potential on the Earth in the form of oxygen. This doesn't happen unless you have manganese around, because if you look at those E values, it's very hard to have something that's going to be abundant, that's going to have an E value that will allow you to make that much oxygen. So it all comes together and is centered around manganese and oxygen. So that is part 1.